Welcome to Code Tuning Forever, the place where system design goes beyond abstraction. Too often, designs are explained in theory, leaving you wondering how they actually hold up in the real world. And that's where we come in. Here, we dive deep into architectures, break down abstract concepts, and connect them to real-world examples backed by benchmarks and performance insights. Whether you're a student, a developer, or a curious engineer, this channel is about sharpening your understanding of systems by tuning them against reality. No fluff, no hand waving, just clear explanations, practical demonstrations, and the kind of depth that makes you say, now I get it. So if you're ready to move past the surface and explore system design the way it was meant to be understood, hit that subscribe button and join me on this journey. Welcome to Code Tuning Forever. Let's go beyond abstraction together. In this video, I'm going to walk you through the website system design in greater detail, but from a staff level perspective, grounded in real-world scenarios. Many videos out there explain this design in a purely abstract way. To go deeper, I've studied two of the most influential approaches from Hello Interview channel and Jordan Hanson Live channel. Each of them outlines the functional and non-functional requirements. As you can see, the four main features will be: users should be able to send message on one-to-one chat. Users should be able to create group channel. Users should be able to send message on one-to-many chat. And the last one, online presence. On the right side, the non-functional requirements. Low latency. A user should be able to send a message in lower time, 500 milliseconds, in a high concurrency. And the system should be able to handle 3 billion active daily users. The first system design we're going to deep dive is the Hello Interview design, where this guy set a load balancing to handle requests from millions of users. The chat server manages the WebSocket connections, and to communicate between chat servers, giving to clients connected to different chat server is done by using the Redis pub and sub streaming. The database is DynamoDB, which is a managed service on the AWS cloud provider. It's a managed service, and S3 is used basically to upload images, and then it returns the signed URL for a given image to then be stored on the DynamoDB to then be shared to another user. I'm going to be focused on the chat server that is the core of the architecture. This guy use Redis pub and sub. That is a simple glue. Redis is often used as a sidecar to languages like Node.js or Go to synchronize messages across multiple service instances. It offers low latency. In-memory speed makes message delivery near instant. Massive throughput, which means handles millions of operations per second with minimal overhead. As this disadvantage is ephemeral nature. It means the Redis pub and sub is fire and forget. For example, if a user's WebSocket connection drops for a millisecond, the message is lost. Back pressure issues. If a subscriber is slow, Redis can buffer messages until it until it runs out of memory or starts dropping data. But what about the real world? Let's say currently the WhatsApp architecture handles about 3 billion users per day. Let's say we're gonna implement the chat server cluster using Golang, and the Golang servers communicate through Redis pub and sub cluster. Given some benchmarks, one instance running Linux with 32 core CPU and 64 GB RAM in Golang supports about 100,000 users per day. So when we calculate, the platform will need 30,000 instances running. But when we see the calculator estimated in the Google Cloud, we received the cost $26 million per month. So it shows a huge amount of cost. In the real world, is so much more expensive. So we have to suggest a better approach. So in this case, Erlang is the go-to way, because Erlang doesn't just send messages. It manages the entire life cycle of millions of individual connections as isolated processes. It handles extreme concurrency, one Erlang process per user. WhatsApp family handled 2 million connections on a single server using Erlang. So the platform would need only 1,500 instances running. So we don't need an extra layer. So the users will be able to communicate between them using the same process ID that is cheaper than the Golang and the Redis integration. So based on that being said, the cost for 1,500 instances would cost $1 million per month. As evidence, I'm gonna leave some links that support my conclusion. The second system design is from Jordan Has Live channel. He chose Cassandra as a data storage for handling user presence and the contact ID and location ID. For Cassandra has its own advantages and disadvantages. It offers availability versus consistency. Cassandra is designed to be always on. In the event of a network partition, it prioritizes allowing writes and reads over ensuring all nodes have the exact same data simultaneously. The second one is the write performance and read flexibility. The data must be modular, especially around the query patterns. Unlike SQL databases, you cannot easily perform joins or ad hoc queries without destroying performance. And the second one component is the load balancing. He chooses round robin algorithm for the load balancer. Using round robin for WebSocket load balancing involves trading off perfect real-time load distribution for simplicity and low overhead. Um, the issues with round robin is the uneven load distribution. It could be a bottleneck because WebSocket connections can stay open for hours. So one server might end up with 100 active high traffic connections, while another server has 100 idle low traffic connections. Another one is the auto scaling inefficiency. If a new server is added to this cluster, round robin will not immediately fill it up. It only sends new connections to it in turn, leaving the new server underutilized while older servers remain overwhelmed. So standard round robin is often insufficient for production WebSockets applications. So I suggest to use least connections. This is generally superior to round robin for WebSockets because it directs new connections to the server with the lowest number of active connections. So that being said, Discover basically decided to move from Cassandra to ScyllaDB to eliminate high operational toil and unpredictable latency caused by Java garbage collection and compaction issues. ScyllaDB's C++ architecture offers superior, consistent performance, reducing node count from 177 to 72. As you can see, there are many key reasons for migration. One is the JVM garbage collection process. Cassandra's dependency on the JVM led to several GC processes, causing high latency spikes during peak usage. Unpredictable tail latency. So the best approach to implement this architecture is the following. By implementing the chat connection using WebSocket implemented in Erlang, where each connection represents a process and every process is communicated by using the virtual machine of Erlang named Beam. Each client's WebSocket is handled by a dedicated Erlang process, PID. That process is the entry point of all message types. So we can deploy many clusters for handling WebSockets. But if you want to handle the group chat, we can deploy another cluster named group chat. So we can route the messages based on the message type. Messages arriving from the client include metadata. For example, the type and the contact ID and payload. The Redis clusters keeps the contact location. So the content is the PID where the actor is located in a given server, the node, and the status that it can be online or offline. And when there are many users connected to the same server, let's say a group has more than 1,000 users connected, a good way is using a sharding that coordinates the all coming traffic from the client flows into its single session process. And by doing that, we can prevent a pain point of failure. So that's it. I hope you enjoyed the video. See you later.